Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Chris Jackson. And Fred was talking about a question about an extreme aging or testing problem.
So somebody asked a question about electronics, and it was basically, and it wasn't from a museum. It was some other organization. I don't have a whole lot of details, but what do we need to? Is it possible for LED, for example, or a CMOS chip, memory chip, for example, that has PN junctions, basically? Can we put those on the shelf and store them, in oxygen-free environment, steady temperature, that kind of stuff, basically in a vault underground someplace, for 200 plus years? And would it still work? And he said, we're not finding anything where people do shelf life studies at those durations. Like, It's kind of, most electronics hasn't even been around for 100 years
Right.
of any form whatsoever, even the old analog stuff. And most products are made for, single use, 5 years, 10 years, maybe 20 years. I don't know. What's the spacecraft Voyager? It's been out there for like almost 40 years or something like that.
Yeah, it's pretty incredible. It's still working. And one of the reasons it's still working is it's quite simple.
Yeah.
Compared to what they're doing now.
Yeah. But that would be probably our best study of, but I'm sure it's shielded to some extent from just basic radiation. Otherwise, I think it would probably fail pretty quick.
Yep, absolutely. But it's a beautifully simple design. Mm-hmm. It's easy to make things hard. It's hard to make things easy.
Right. Well, here's the dilemma: is how do you take say a projector or a laptop computer off the shelf today, and you store it under controlled environmental conditions to what you can control, and would it work? And my first thought is, unless it was made in a clean room, it's going to be covered in bacteria. And then you take away the oxygen, and then the bacteria that loves to live in an oxygen-free environment, anaerobic stuff, is going to eat everything that it can digest. And that includes polymers. They will break those down and eat them. And it might take them a long time to do it, unless you can actually get rid of them all and then don't touch it again. Or, it's like super clean room things to get bacteria off of stuff. Or if you put a fingerprint on it, not even you, if it's in manufacturing, somebody sneezed, now you got contaminants that some of which can create corrosion without oxygen or with voltage. It just takes a long time. And so my head started reeling of, well, what are the failure mechanisms we just ignore now because of their time scale? And that when you go an order of magnitude longer, become an issue.
So why do they need to know the shelf life out to 250 years?
I don't know. The one sentence was, well, we want the media that we're storing, we want to have a way to play it, so that they could. And I'm thinking, what are they going to plug it into?
Mm-hmm.
It's making the assumption that you still got power outlets. What do you do with this pointy thing on the end of this cable? My first thought was modern day off the shelf, go down to Best Buy and buy something and stick it in a bag is probably just not going to work. Not because it itself, even if you assume all the electronics still work, right? That the capacitors didn't dry out, that the polymers didn't diffuse away, the PN junctions didn't lose their difference and holes in active regions, and it diffused out, or dielectrics didn't erode and flake off. Even with very, very, very small thermal differences, that cracking and separation can occur. Adhesives will, fail, become brittle. Yeah, it would be faster if you stick them out in the sun in, an oxygen-rich environment with lots of seawater. But I'm thinking there's a whole pile of stuff that happens to silicon that just takes a while to happen. And I don't know the timescales of which, they do a lot of testing where it's high temperature and high current densities and all this other stuff to excite these things. But what I don't know is I don't know enough about these different failure mechanisms that we commonly address. At normal temperatures, is this time scale in the order of decades, or is it an order of centuries, or an order of millennia? I don't know which ones apply, because there are some failure mechanisms that only occur once you get the enough energy into the system, whether it's temperature, current, or stress, or whatever, for it to start. Right. But there's some that, like diffusion, will occur even at very low temperatures. It's just slower.
Right. It's never an on-off valve. It's just a flow rate valve.
Right. So part of it is, so one of my thoughts was, what are the latent defects, like ESD, for example? You could take a perfectly good one. It's working in the process of packaging it up. Somebody doesn't pay attention to ESD and they zap it and they put it away and it's dead. And they won't find out until they try. Then I said, well, there's a whole class there. Then there's a whole class of just physics and chemistry that will occur. And that's the part I'm not finding a whole bunch of any information on it, and I need to dig more into it. Then there's a whole realm of, if you're worried about just the CMOS PN junction, what about the capacitors? What about all those other components? There's a lot of other places that things can fail. And then beyond that is, the polymer and the structure, the circuit board, all of these pieces, how long can they last? And then do you have a system to actually power it? Are we still going to be using 120 volt AC power outlets, or is that even going to be available? And then you need to have a generator or something to create power that you can do it, or instructions how to do it. Well, how about instead of having one device, get another device that uses a completely different technology, so have two groups of things you don't know about, or better yet, have a whole set of specifications of how to build your own,
right?
To do the same function, but they can figure out a way to do it. And they're like, what's the right way to approach this kind of question when they're starting with, well, how do we take an off the shelf thing and figure out whether it'll work 250 years from now or 500 years from now? I'm better at figuring out if it'll still work in 10 years, but I never thought about over 100 years.
I remember seeing some probabilistic risk assessments for nuclear power plants where certain failure modes, if you looked at the frequency curve, so for all intents and purposes, a bell curve describing the likely frequency at which the failure modes were going to occur based on the probabilistic risk analysis. Some of the tails were exceeded 14 billion years, which is older than the universe, and so it's just interesting that as I've seen plenty of detailed analyses, and we always espouse detailed analyses. You always espouse using your corporate knowledge, and if you've got expert judgment there, use it. If you've got test data from similar systems, use it. If you don't know, test yourself and then use that information. We're a big fan of using information, no matter where it comes from, as long as it's clean, so to speak. Yeah. Incomplete doesn't make it dirty. But then you see scenarios where you go, okay, how the hell can you, with any level of confidence, suggest that a failure mode, a nuclear power plant, is going to occur once every
universe
lifespan? And we have had multiple nuclear power plant accidents in the relatively short time frame they've been a thing. Yep. And it's funny listening to people say, oh, that doesn't count because, the analysis is based on these premises and assumptions. And you go, you know what? Your report is actually every reliability report or every probabilistic risk analysis. It has to be useful, which means that there aren't caveats, that there aren't assumptions, or the assumptions are, transparently understood and understandable. But if you, I suppose, but going back to the problem at hand, we need to have some sort of test that allows us to look at whether a certain thing's going to be working 250 years from now. The one thing that for me, I should say, is going in the favour of the listener who's asking this question is that their component or system is a lot simpler than a nuclear power plant, which is a good thing.
Yeah.
That means you're able to model it in a way that you can extrapolate beyond typical human experience with some confidence.
Well, that's the rub, though, Chris. Is you just exposing it to high temperature, which doesn't even work to give you a reasonable estimate out to 10 years if you've got multiple failure mechanisms, right? So that's the first part is if we're going to set up a test or we're going to look for research or studies or stuff, is vast majority don't really care about after. A lot of them, frankly, don't care much after you get it off the production line, but out to 10 years or 20 years, it's kind of like, and that's active, light up the light bulb and you get 2,000 hours and, oh, okay, that's good. But how long can you keep that incandescent bulb on the shelf before it fails? And there's some that you take out of the box and plug in and it doesn't work. And that could be a latent defect. It could have been damaged in transit. I mean, there's all kinds of scenarios where just on the shelf it fails. And that's the part I'm struggling with is interpreting, does hot carrier injunction, I think, actually needs current to actually occur. Whereas hole depletion or delamination or, if the passivation layer is not perfectly matched to the substrate, even small variations over time will separate it, I think. And it's kind of digging through which of these failure mechanisms that we have models for, that we have, physics of failure understanding for it, and this, that, and the other thing are relevant when we go to very low stress. That's the part I'm struggling with but it's also, what do you look for? Do the mastodons come back and then they stomp through your warehouse? That would be considered for a nuclear power plant, I imagine. But for electronics, I'm trying to think through the just tons of different ways they fail and that we pay attention to in the design and manufacturing of these things. I mean, if there's any impurities at all in those junctions, will that in and of itself cause decay of its ability to perform as a junction?
Well, I'm talking to a client who's sort of dealing with this problem in terms of accelerating testing for a system which involves very precise laser, and amongst a bunch of other things that deal with the information generated by said laser. And it's a very sophisticated piece of kit, but on one level, but on the other level, it's very simple. And you talked about imperfections, and the problem. I mean, we were reviewing vendor data where they essentially said, these first 3% of failure data points under accelerated testing, they clearly don't fit the rest of the data, so that's infant mortality, so they don't count. I think we've had this conversation many times. In fact, they're the only ones that do count, because usually when your system reliability drops below 90%, it's done. It's no longer useful or feasible to keep having or keep using. And so if you've got hundreds of components, then they need to have reliabilities that exceed 99% before the system starts becoming obsolete from a supportability perspective, which means that virtually every failure you're going to observe that matters, if failure is driven by electronic componentry, is something that is based on this thing called infant mortality. The other problem with electronic components is that when we use the word infant mortality or wear in, we often simply jump to manufacturing defect or assembly error. But manufacturing electronic components is damn hard. Even if you have the most perfect manufacturing scenarios, so many of these components are based on essentially what are hoped to be very pure crystal structures.
Yeah,
and
which they're not.
Which they're not. No, exactly right. Ideally, you want to have a single grain for many of these applications, and their manufacturing process is getting better and better each day at making those grains bigger and bigger and bigger. Still not going to have a single grain for every single component you manufacture, which means that even best practice, you're going to have a subset which have more defects than others. And so not only do you want to accelerate, but you actually want to know what sort of part of the failure spectrum you are accelerating. So with this client in particular, we're just advocating we actually disregard the large body of data that shows, let's just call it typical end of life wear out. The only failures you're interested in are these seemingly small, insignificant, less than 5% of failures, which have their own failure characteristics at the very start. They have their own. It's actually better to describe them as early wear out because this doesn't have that decreasing curve. There's such simple components that when you have infant mortality for such simple components, you tend to see what appears to be early wear out for a subset of components versus that bathtub curve. That's a whole nother podcast right there, I believe. But but that's what you need to focus on. So far from being able to extrapolate based on, let's call it, the perfect steady state design intent state of play, you actually often really need to focus on how those imperfections are on your day, because they're the ones that drive the reliability metrics that matter.
Yeah. And I've heard that complaint actually from Kirk. He's like, if you can make one that works, electronics will probably keep working for the period of time you're interested in. And if you ignore all the early defects, you kind of combination pissing off your customers and you're ignoring the parts of the process that, it says, well, but all these prediction methods and all this accelerated testing and all these physics of failure models and stuff, they all focus on the end of life. And Kirk's like, who cares? It's like, if you can't transport it where it still works when it gets there, it really doesn't matter. It's not going to get to the end of life, and you can't just ignore that stuff. And I've run into clients like that. It was, that happens and we don't have to worry about it. Yeah, it's 10% of your product. It doesn't make it. I had one that was 50%. And like, yeah, we just have to send another one. It's like, why don't you pay attention to that? But that's kind of the dilemma I'm struggling with is that, normally when I sit down and do an accelerated test of any kind, it's, well, what time period are you looking for? Is it early life type stuff? Are we looking at doing that? Are we looking at trying to expose what's going to fail, or to survive transportation? Does it do this, do that? And then they say, well, we got all that under control, or we think we got it. We need to know if it'll last the 5 years of our warranty or not. Are we financially too exposed or not? What's the likelihood? And like, okay, you have a good rationale behind it. All right, now what's likely to fail? That's usually my first step is what's the fault tree look like, and what's your dominant failure mechanism or handful of mechanisms? Because it's near impossible I'd say it's impossible to select a way to test it if you don't know what the mechanism is.
Right. Especially 250 years from now, when the mechanisms might change or be something we haven't studied.
Yeah. I hadn't even thought about that part. I'm starting with the premise of what is it that we do know that, if there's, I'm thinking of tin whiskers. They don't take anything to occur. And as far as I know, we've learned a lot about that. If you put plate tin on a surface and then it's formed or bent or something like that built-in stress of that deformation and then you can't cure it out, you can't burn it out or anything else, you can't relieve that stress in any meaningful way. That's one theory as what causes them to occur. It's kind of, they can replicate it. So last I heard was that we think we know that that's what causes it to occur. But what other phenomena, will grow out of all of these? Because so many, if you look inside an electronics box, there's a lot of bent stuff. There's a lot of surfaces matching. There's a lot of, all kinds of different phenomena that are under some form of strain or stress. What's the right word? Is it strain or stress? When there's a tension between two things.
Or that's stress. Stress induces strain is like the physical change.
Okay.
Stress is the actual pressure.
Okay. So
associated.
I'll use pressure. There's this, in general, when you get down to it, the second law of thermodynamics doesn't like that kind of state and says we're going to relieve that pressure. We're going to reduce that stress. And that sometimes it's diffusion, sometimes it's cracking, sometimes it's whatever. And that's the stuff I'm thinking is probably going to turn this electronics box into a pile of dust, is just the basics of second law of thermodynamics.
Absolutely. It really is a challenging scenario. It's 250 years. That's a long time. And I'm guessing they haven't come to you with, here are the things that are going to keep us up at night.
No. Well, I mean, it's the first one was, should we put an extra light bulb in there with it? Do a backup for the things we think are going to fail. It's like, well, if you thought about the capacitors, if this is a, power supply, it's got to kick out a bunch of current. It's probably got electrolytic capacitors in there. And we know that shelf life of those things is on the order of 15 to 30 years. Just,
right.
So I'd worry more about those because we know those don't last. And we get one that uses solid state ones. All right. Well, polymer based ones, they're a little better, but they still have the same mechanism where that dielectric fails. I also think, like this weekend, there's here in California or in the news this morning when I was looking through it, they were saying that some parts of North America would be able to see the northern lights this weekend because of solar flare activity like a week ago or something like that. There's going to be a kind of the conditions are right to see is it Aurora Borealis? Something like that. I think it's the northern lights. You probably have a better chance of seeing them than I do.
Maybe, yeah. In the southern hemisphere, it's Aurora Australis.
Where'd that name come from? What's the big
Australis
country down there?
Well, that's Australis essentially means south. So Australia means southern land.
Oh, right.
That's where you see this. There you go. So that's where you hear a lot of Australopithecus and Australis in Australia. It tends to refer to things from the south.
Oh, okay. I had no idea. That's cool. But solar radiation, and we know that neutrinos are very difficult to detect, much less cause anything to occur, but they do. On occasion, they bump into something and go, you go left now, I'm going right. And we can detect those. There's a whole range of other radiation that has amazing penetration powers, and is very rare that it causes damage. Yet we know from electronics that if you're in Denver, you have a much higher probability of getting a memory faults because of, I'm trying to remember if it's neutron or some other form of radiation can wipe out 4 cells in one shot. And folks are figuring out how to recover from those. They can do 1 cell easy, but when you get 4, it gets real tricky. And that doesn't take, it just takes shielding. But even the best of shielding doesn't protect against the ones that are more rare and, can cause damage. That's where my thought process about, there's lots of ways things can fail is now it's just wide open. If you give me 100 years to work on it, there's probably an order of magnitude more ways of things can fail. So I'm like, okay, this is a challenge.
Yeah. It's so. What are you going to do?
Well, like the very first test I did is, I'll take a couple hundred of these devices and go to northern Italy and watch them for the next 150, 200 years and see if I can get a good estimate for them.
In some sort of vineyard, no doubt.
Oh, yeah, nearby. It's got to be. That's the perfect storage conditions. I mean, we can store wine for 100 years. We can store, maybe that's the trick. Just store it in a big barrel of brandy,
That's actually, we got there completely fortuitously, but wine's not a bad analogy or proxy for some of the things we're talking about, because how do we know how to store wine? Because we know how it goes bad.
Mm-hmm.
And so you have all sorts of wine bottles which need to be stored the right way up or upside down or rotated every year or so, et cetera, et cetera, et cetera. Why? Mm-hmm. Because the winemakers know how that wine can go bad. It's actually a great example of, you can hand the problem off as much as you want, but it wasn't as if there was a laboratory who back in Renaissance Europe, there was no wine laboratories there trying to do tests to work out, statistically how do we characterize how wines degrade over time. No, the winemakers said, well, if you do this, it's going to go bad, so let's not do that. Yeah. And all of a sudden, they worked out how to store wine for a long period of time. It comes back to, dare I say it, the designers, so to speak, the winemakers that, in a way, design the wine, and they have to know how to make great wine, which means they also know how it goes bad.
Yeah. I guess it comes down to what could go wrong. Well, it starts with just brainstorming it and thinking beyond the current day, focus on what will kill it in 5 years. It's what will make it go bad over the longer term. So anyway, it's been an interesting, I've been puzzling over this for a couple of weeks now, it seems like, and I'm like, it's still not any closer. Every time I start looking into it, it just explodes into, well, there's a whole pile of possibilities here. And then I start digging into the technical papers and they're like, okay, I have no idea what they're talking about here. It's, at the interface of the apixel and epixel layers, and it's, coated with this, exotic chemical and etched with this. And I'm like, what component is this even on? So it goes, and some of them are papers as they develop the processes to make things. And he says, well, if you don't pay attention to these details, then you're going to create problems right off the bat. So you got to deal with that. And so it's been designed out right from the start. And others are latent defects. And I'm like, is that meaningful or not? What's that? So the thought process goes on. It's been an interesting diversion here for my summer reading, I guess, of figuring this one out. So maybe that's the title, is What Could Go Wrong? So anyway, I know I'm not any closer than where I was, but a couple of ideas, a couple of thoughts there, and maybe a glass of wine this afternoon will help sort out what the right move here is.
Well, I think the conclusion is wine is always good. One helps.
What else? Yeah, it'll work. All right. Well, I know I've talked about this at an earlier podcast, and I'm still kind of playing with it. So I'm looking for some insights or ideas or pointers of the perfect paper somebody, took a wine barrel and aged it for 200 years, and how did it go? We'll go with that. Head over to accendoreliability.com/go/SOR. You can get in touch with us. Chris and I and the other hosts of the show are available through LinkedIn and our About pages. Lots of ways to get in touch with us. And some questions just puzzle the daylights out of me anyway. So if you got one like that, send it on over. Keep the diversions going for me. That'd be cool. But with that, I think, Chris, we'll have to come back in a couple hundred years to see if this laptop still works.
That's right. Sando was aged.
That's right. We'll see how it does. All right. Well, thanks much, Chris. Talk to you later.
Have a good one, Fred.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.